Welcome. This is a compiler design mock test, 10 advanced questions. But here is the twist, every single question has two statements. One may be true, both may be true, or both may be false. Your job is to figure out the exact combination. These are not easy questions. These are the kind that separate students who truly understand compiler theory from those who just memorized it. Get a pen. Stay focused. Let us begin. Question 1. Two statements about compilers and preprocessors. Statement 1 says, a compiler performs code optimization, but a preprocessor does not. Statement 2 says, a compiler performs full syntactic and semantic analysis, but a preprocessor does not. Now here's what you need to think carefully about. Both statements are talking about what a compiler does versus what a preprocessor does. The question is, are they both correct, or does one of them cross the line into territory that does not belong to either? Make your choice, A, B, C, or D, and move on. Question 2. Statement 1 claims, lexical analysis is recursive, specifically to handle nested parentheses. Statement 2 says, scanners do not know anything about the grammar of a language. Think about what a lexical analyzer actually does at its core. Does it use recursion? Does it even have a stack? And what exactly does a scanner see when it encounters your source code? This one has a very common misconception hidden inside it. Lock in your answer. Question 3. Statement 1. A successful pass means the input is semantically correct. Statement 2. Transition tables are indexed with current state and next state. Two completely different topics in one question. That is intentional. On statement 1, think carefully. Just because parsing succeeded, does that guarantee the meaning of your code is correct? On statement 2, think about how a transition table is actually structured. What are the rows? What are the columns? Choose your answer. Question 4. Statement 1 says, syntax analysis handles type checking and type conversions, like converting integer to float. Statement 2 says, parsing is a linear representation. This is a question about which phase of compilation does what. Many students confuse syntax analysis with semantic analysis. Are they the same? Absolutely not. And for statement 2, think about what parsing actually produces and how the input is processed. Your answer, A, B, C, or D. Question 5. Statement 1, a sentence with more than one production tree is called ambiguous. Statement 2, an ambiguous string is spuriously ambiguous if all its production trees describe the same semantics. This is about grammar ambiguity, one of the most important and most misunderstood topics in compiler theory. Pay attention to the word, spuriously. It has a very specific technical meaning here. Do not guess, reason it out. Finalize your choice and proceed. Question 6. Statement 1, an ambiguous string is essentially ambiguous if its production trees differ in semantics. Statement 2, a grammar is essentially ambiguous if it can produce an essentially ambiguous string. We are now going deeper into the two types of ambiguity. The key word is, essentially. How is essential ambiguity different from spurious ambiguity? Think about what semantics differ actually means in this context. Mark your answer. Question 7. Statement 1, a grammar is spuriously ambiguous if it can produce a spuriously ambiguous string, but not an essentially ambiguous one. Statement 2, LR1, parser processes input symbols from left to right. Two topics again. Statement 1 is the definition of spurious ambiguity at the grammar level. Think about whether this matches what you have learned. Statement 2 is about LR parsers. What does the L in LR actually stand for? Choose wisely. Question 8. Statement 1, left factoring is a technique to prepare a grammar for use in a recursive descent parser. Statement 2, left factoring is a technique to produce a leftmost derivation of a string from a grammar. Both statements are about left factoring, but they are making very different claims about what left factoring actually does. Statement 1 sounds right, but does statement 2, does left factoring have anything to do with producing derivations? Think carefully, this is a trap. Question 9. Statement 1, left factoring can remove left recursion from a grammar. Statement 2, left factoring can factor out left associative operators. Both sound plausible. That is exactly the trap. Left factoring and left recursion removal are two different techniques that are often confused with each other. Do they overlap? Can one do the job of the other? This is one of the most commonly confused topics. Choose your answer. Question 10, the final question. Statement 1, LR1 parsers are less powerful than SLR1 parsers. Statement 2, LR1 is a subset of LALR1. This is about the power hierarchy of parsers. There is a well-known ranking. If you know it, this question is straightforward. If you do not, one of these statements is going to trap you. Think, where does LR1 sit in the hierarchy compared to SLR1 and LALR1? Lock in your final answer. The answer key is next. Time to check your answers. Part 1, questions 1 through 5. Look at each answer carefully. If you got them all correct, excellent. You have a strong grasp of the fundamentals. If you missed one or two, do not skip the explanations. That is where the real learning is. Check your score for the first 5 questions now. Part 2, questions 6 through 10. These were harder. They tested your understanding of ambiguity types, left factoring, and parser hierarchies, topics that many students read but very few truly understand. Check your answers. Then stay with us, the explanations that follow will make these concepts permanently clear. MCQ 1. The correct answer is option C, statement 1 is false, statement 2 is true. Let us take statement 1 first. It says, a compiler performs code optimization, a preprocessor does not. The first part is correct, a compiler absolutely performs code optimization. But the second part, that a preprocessor does not optimize, is where this statement fails. A preprocessor enables encapsulation and simplification of complex details without the overhead of functions or objects. That is a form of optimization. It also enhances code reliability and readability. So saying a preprocessor does nothing related to optimization is not accurate. Statement 1 is false. Now statement 2, a compiler performs full syntactic and semantic analysis, a preprocessor does not. This is completely correct. A preprocessor only does textual transformations, removing comments, including files, defining constants, substituting macros. It does not analyze grammar. It does not check meaning. That is entirely the compiler's job. Statement 2 is true. The trap in this question was statement 1, it sounds right, but the claim about the preprocessor is wrong. MCQ 2. The correct answer is option C, statement 1 is false, statement 2 is true. Here is the key concept, lexical analysis is not recursive. A lexical analyzer, like Lex, works with finite state machines, and finite state machines have no stack. Without a stack, you cannot handle recursion or nested structures. Nested parentheses require a stack, that is the job of the parser, not the lexer. Statement 2 is completely correct. A scanner only produces tokens. It has no knowledge of grammar rules. Whether an opening parenthesis is ever matched with a closing one, that is not the scanner's problem. That is the parser's job. MCQ 3. The correct answer is option D, both statements are false. Statement 1 is a very common misconception. Parsing checks syntax, the structure. It does not check semantics, the meaning. You can write code that parses perfectly and still makes no logical sense. Semantic analysis is a separate phase entirely. Statement 2 is also wrong. Transition tables are indexed by current state and input symbol, not next state. The table tells you, given this state and this input, what do you do next? The next state is the result, not the index. MCQ 4. The correct answer is option C, statement 1 is false, statement 2 is true. Statement 1 is wrong. Type checking and type conversions belong to semantic analysis, not syntax analysis. The semantic analyzer works with the parse tree and the symbol table to enforce type rules. Syntax analysis only checks the structure of the code. Statement 2 is correct. Parsing is a linear representation process. It takes a linear sequence of tokens and arranges them according to grammar rules. The input, whether it is a sentence or a program, is always a linear string. MCQ 5. The correct answer is option A, both statements are true. Statement 1 gives us the definition of ambiguity itself. If a string can be generated by a grammar in more than one way, producing more than one parse tree, that string is ambiguous. Straightforward. Statement 2 introduces a specific type, spurious ambiguity. The keyword here is same semantics. If two different parse trees for the same string produce the same meaning, same result, same behavior, then the ambiguity is harmless. That is spurious ambiguity. Both definitions are correct. MCQ 6. The correct answer is option A, both statements are true. This is the flip side of spurious ambiguity. If two parse trees for the same string produce different meanings, different semantics, then the ambiguity is not harmless. It is essential ambiguity. And if a grammar can generate even one essentially ambiguous string, then the grammar itself is called essentially ambiguous. Both statements are textbook correct. MCQ 7. The correct answer is option A. Both statements are true. Statement 1 defines spurious ambiguity at the grammar level. A grammar is spuriously ambiguous if it produces spuriously ambiguous strings, but never essentially ambiguous ones. That is a very specific and clean definition. Statement 2 is about the LR1 parser. The L stands for left to right scanning of input. The R stands for rightmost derivation in reverse. And the 1 means one symbol of look ahead. All three parts confirm that the input is processed left to right. Before we move on, a quick summary of ambiguity types, because these concepts appeared in questions 5, 6, and 7. 1. A string with more than one parse tree is ambiguous. 2. If all those parse trees give the same meaning, that is spurious ambiguity. Harmless. 3. If the parse trees give different meanings, that is essential ambiguity. Dangerous. 4. A grammar inherits these labels based on the strings it can generate. This hierarchy is fundamental. Remember it. MCQ 8. The correct answer is option B. Statement 1 is true, statement 2 is false. Statement 1 is correct. Left factoring transforms a grammar into a form that a predictive or recursive descent parser can use. It removes the ambiguity that arises when two productions start with the same symbols. Statement 2 is wrong. Left factoring does not produce leftmost derivations. It restructures the grammar. Producing leftmost derivations is what a parser does during parsing, it is not what left factoring does to the grammar itself. Different tools, different purposes. MCQ 9. The correct answer is option B. Statement 1 is true, statement 2 is false. Statement 1 says left factoring can be used to remove left recursion from a grammar. This is true. Statement 2 says left factoring can be used to factor out left associative operators. This is false. Left factoring has nothing to do with left associative operators. These are two completely different concepts. The danger in this question is that both statements sound related to grammar transformation, so students assume both are true or both are false. That is the trap. Remember, left factoring is specifically about resolving common prefixes in production so a predictive parser can decide which rule to apply. It does not handle operator associativity. A critical concept: why does left factoring exist? Predictive parsers need to decide which production to apply by looking at the next input token. If two productions start with the same symbols, the parser cannot decide. That is the problem. Left factoring solves this by pulling out the common prefix into a new non-terminal and leaving only the differing parts in separate productions. Classic example: the if-else statement. After left factoring, the parser can check whether the next token is else and decide accordingly. Left factoring is about resolving parser indecision, nothing more. MCQ 10. The correct answer is option C. Statement 1 is false, statement 2 is true. Statement 1 is completely wrong. LR1 parsers are actually more powerful than SLR1 parsers, significantly more. They handle a larger class of grammars. Statement 2 is correct. LALR1 is based on LR0, and LR1 is a superset of LALR1. So yes, LR1 contains LALR1, which means LALR1 is a subset of LR1. The power hierarchy, from weakest to strongest, is LR0, then SLR1, then LALR1, then LR1. Know this hierarchy. It comes up everywhere. Final note, and this one is worth writing down. The parser power hierarchy from weakest to strongest: LR0, SLR1, LALR1, LR1. Each level can handle a larger class of grammars than the one before it. LALR1 is particularly important in practice. It is used in most real compilers because it offers nearly the power of LR1 with far less memory. The foundation of LALR1 is LR0 with added look ahead. That is the design philosophy behind most modern parser generators. Thank you. That is your compiler design mock test complete. How did you score? Let us know in the comments, and if these questions challenged you, share this with someone who thinks compiler theory is easy.